In the autumn of 1799, in the towns of Massachusetts, American builders moved entire two-story houses across the soil. Workers relocated these timber-framed structures using heavy wooden carriage systems and log rollers. A standard two-story wooden house of this time measured roughly 20 feet wide by 30 feet long. The building materials, including the heavy oak frames, the wide pine floorboards, and the thick plaster walls, weighed approximately 15 tons. Builders began the relocation process by severing the structural connections to the original fieldstone foundations. The workers used iron hand saws and heavy iron crowbars to pry the wooden sills away from the dry-laid stones. The carpenters dug shallow trenches around the base of the house, using flat iron spades with wooden handles. The iron shovels scraped against buried stones, ringing out in the morning air. The men cleared away the topsoil to expose the underside of the floor joists. Next, the workers inserted broad squared timbers of eastern white pine under the wooden sills of the home. These parallel beams, measuring 12 inches thick and 40 feet long, formed a continuous wooden sled beneath the structure. Men positioned cylindrical wooden rollers underneath this sled. The builders shaped these rollers from solid white oak logs harvested from the local forests. They stripped the rough bark with steel drawknives to create smooth 10-inch diameter cylinders. The dense grain of the white oak supported the 15-ton weight of the house, maintaining their exact cylindrical shapes under the immense pressure. The wooden rollers rested directly on parallel tracks of flat pine planks laid across the grass. The planks, measuring 3 inches thick, distributed the heavy load over a wider area of ground. These flat tracks kept the heavy oak cylinders resting on top of the soft earth and mud of the Massachusetts fields. To move the building, the crews harnessed teams of draft animals to the forward ends of the pine sled beams. The builders favored teams of oxen for this heavy work, connecting 4 to 8 animals in a single line. Farmers carved thick wooden yokes from hickory to fit across the broad, muscular shoulders of the oxen. The smooth hickory wood pressed firmly against the animal hides, transferring the entire weight of the pull to their necks and shoulders. Thick leather straps attached the wooden yokes to long, forged iron chains. The chain links, measuring 1 inch thick in diameter, stretched back toward the house. The workers linked these heavy iron chains directly to forged iron rings bolted securely into the front of the pine sled. The drovers walked beside the animals on the dirt, holding wooden driving sticks. They shouted physical commands to guide the beasts forward. The oxen leaned into the yokes, digging their split hooves deep into the dirt and grass. The heavy iron chains lifted from the ground and snapped rigid under the massive tension. The animals generated a massive horizontal pulling force. This pulling force transferred straight down the iron chains and pulled directly against the wooden beams of the sled. As the sled moved forward, the smooth white oak rollers began to rotate beneath the heavy pine beams. The 15-ton timber house rolled forward across the fields at a rate of a few inches per minute. The heavy oak cylinders crushed the autumn grass, releasing the smell of damp earth and broken stems into the cool air. As the house moved forward, the rear oak rollers emerged from the back of the moving sled. Workers walked behind the house and picked up these heavy wooden cylinders with their bare hands. Each 10-inch oak roller weighed over 100 pounds. 2 men carried each heavy log along the sides of the structure to the front. They placed the logs back onto the wooden tracks directly in front of the advancing sled beams. The continuous manual transfer of the rollers kept the house supported at all times. The teams of oxen continued to pull the structure, foot by foot across the uneven terrain. The bottom surfaces of the wooden carriage ground heavily against the top curves of the oak rollers. This movement produced loud scraping noises that carried across the fields. The friction between the untreated wood surfaces generated heat and required immense, sustained energy from the draft animals. The oxen breathed heavily, expelling visible moisture into the 50-degree autumn air. The solid earth of the path provided inconsistent resistance to the pulling animals. Rocks, tree roots, and shallow dips in the soil caused the parallel track planks to tilt and shift under the weight. When a log roller passed over a buried rock in the dirt, the entire house tilted to one side. The horizontal pulling force of the oxen pulled the structure forward in sudden, uneven surges. The varying exertion of the animals sent sharp physical jolts directly into the structure. The oxen paused, gathered their footing, and pulled forward again, creating a stop-and-start rhythm. These sudden physical jolts traveled continuously through the pine sled beams and up into the wooden framework of the house. The internal structure of a 1799 house relied heavily on mortise and tenon joints. Carpenters secured these intersecting wooden joints by hammering dry wooden pegs through the beams. The sudden horizontal forces pulled with great force at these wooden joints. The movement stretched the wooden pegs against the edges of the pine beams. The house shifted and flexed audibly, with every uneven step of the oxen pulling at the chains. The flexible wooden frames bent slightly, absorbing a portion of the horizontal pulling force. The center of these 18th-century homes contained massive central heating chimneys, built from hundreds of fired clay bricks and thick lime mortar. These central masonry columns extended from the fieldstone foundation on the first floor, straight up through the wooden roof deck. The heavy brick structures possessed extreme structural rigidity. The stiff bricks and brittle mortar held rigid, inflexible forms compared to the surrounding pine and oak wood. The sudden, violent jolts from the pulling oxen transferred directly from the flexing wooden floor joists into the stiff brick columns. The moving earth and the shifting rollers sent horizontal shocks straight into the heavy masonry hearths. In the spring of 1810, across the dirt roads of New England, homeowners attempted to relocate their wooden dwellings using horizontal log carriage systems. A massive masonry chimney stood in the exact center of a typical 1810 center hall colonial house. Masons constructed these central heating structures using locally fired clay bricks and white lime mortar. A standard residential chimney required roughly 5,000 individual red bricks to complete. Each fired clay brick measured 8 inches long, 4 inches wide, and 2 1/4 inches thick, weighing 4 1/2 pounds. The completed masonry column weighed over 22,000 pounds. It rested on a massive fieldstone base in the dirt cellar and extended vertically 30 feet upward, passing through the interior wooden floors and penetrating the peaked wooden roof structure. Local masons bound the stacked clay bricks together using a wet mixture of slaked lime, river sand, and water. As this lime mortar dried in the open air over several months, it turned into a solid crystalline structure. This hardened calcium carbonate bond provided immense vertical support for the heavy weight of the stacked bricks. The cured lime mortar broke easily when subjected to horizontal forces. The wooden pine and oak framing of the house surrounded this rigid brick column from the cellar to the roof line. Carpenters built the wooden floor joists and roof rafters, leaving a gap of only 2 inches around the rough brick surface. When teams of oxen pulled the heavy wooden sleds forward over the New England fields, the solid log rollers shifted unevenly over the rutted dirt tracks. The horizontal jolts from the forged iron pulling chains transferred directly into the heavy white oak sills of the house. The entire wooden structural frame bent and deflected under the immense pulling force. The internal wooden floor joists shifted sideways, closing the 2-inch gap and pressing directly against the outer surface of the central brick chimney. The flexible wooden beams transferred the intense horizontal force directly into the brittle lime mortar joints. The hardened mortar cracked instantly under the lateral pressure. The entire 30-foot masonry column sheared apart at the weakened mortar joints. Thousands of heavy clay bricks tumbled downward into the enclosed interior rooms of the moving house. The falling bricks crashed onto the wide pine floorboards, splintering the dry wood and breaking through the plaster ceilings of the first floor. The physical impact shattered the remaining red bricks, sending a dense cloud of white calcium dust into the air of the dwelling. The fine dust settled on the broken wood, carrying the sharp, dry scent of crushed lime and baked clay. The complete structural collapse of the central chimney occurred within the first 30 feet of a physical relocation. The sudden destruction of the masonry hearth destroyed the central heating source and the primary cooking ovens for the entire structure. To protect the structural integrity of the house, New England homeowners hired local masons to dismantle the central chimneys before attempting a physical relocation. Masons arrived at the homes, carrying heavy forged iron chisels, flat steel masonry trowels, and dense wooden mallets. The workers placed tall wooden ladders against the exterior painted pine clapboards of the house. They climbed the wooden rungs up to the angled roofline, stepping their leather boots onto the split cedar shingles. The masons positioned themselves next to the exposed top of the brick chimney, reaching the highest point of the 30-foot masonry column. A mason placed the flat, sharp edge of his iron chisel directly into the white lime mortar joint located between the top 2 layers of brick. He swung his heavy wooden mallet, striking the flat end of the iron chisel. The iron wedge drove deep into the brittle lime mixture. The applied physical force fractured the calcium carbonate bond, splitting the dried mortar into loose white powder and sharp sand granules. The worker lifted the loosened 4-pound red brick away from the stack with his bare hands. He dropped the freed clay brick into a round wooden bucket resting on the sloped cedar roof shingles. Workers filled each wooden bucket with 10 clay bricks, bringing the total weight to 45 pounds. They tied a thick hemp rope to the curved iron handle of the wooden bucket. A worker standing on the grass below held the opposite end of the thick hemp rope. The mason on the roof lowered the heavy bucket slowly down the side of the wooden house. The rough hemp fibers slid against the painted wooden clapboards, leaving faint horizontal scratches in the white lead paint. The ground worker untied the rope, emptied the intact bricks onto a pile on the damp grass, and sent the empty wooden container back up to the roofline. The masons repeated this extraction process, row by row, working their way down through the wooden roof deck. They moved inside the house, standing on the pine floorboards of the second story, to reach the middle section of the chimney. The workers chipped away the mortar surrounding the brick baking ovens and the large open hearths located on the first floor. They removed over 5,000 bricks from the center of the home over the course of 3 working days. The dismantling process left a gaping square hole measuring 4 feet by 4 feet in the center of the wooden roof and floors, exposing the damp dirt cellar to the open air above. Homeowners stored the large pile of reclaimed bricks on the grass to rebuild the chimney after the house reached its new foundation. The complete removal of the 22,000-pound masonry column left the wooden frame entirely flexible. The empty wooden structure bent and flexed safely as the oxen pulled the carriage across the log rollers. This labor-intensive extraction protected the dwelling from sudden destruction during the horizontal pull. The severe limitations of dragging houses horizontally across the uneven earth forced builders to develop methods of vertical elevation. In the year 1831, a carpenter named James Lewis Pullman lived in the town of Brockton, New York, studying the mechanics of threaded mechanical lifts to move heavy structures with precision. In the winter of 1831, a carpenter named James Lewis Pullman worked in the town of Brockton, located in Chautauqua County, New York. James Lewis Pullman built wooden houses and studied mechanical engineering methods in his local workshop. He cut native eastern white pine and red oak timbers using steel hand saws to construct residential frames. His wife, Emily Caroline Pullman, lived in their wooden home near the shores of Lake Erie during the freezing winter months. On March 3, 1831, Emily Caroline gave birth to their third son, George Mortimer Pullman. The temperature outside hovered near 30 degrees Fahrenheit as wood smoke rose from the brick chimneys in the small agricultural settlement. The infant George Pullman weighed roughly 7 pounds at birth and slept wrapped in woven wool blankets inside the wooden house. James Lewis Pullman sought a mechanical method to lift heavy wooden structures vertically off their fieldstone foundations. He reviewed the geometric principles of the simple machine known as the screw. The Greek mathematician Archimedes documented the physical mechanics of the screw while studying in Alexandria, Egypt, around 234 BC. Archimedes observed agricultural workers using a wooden cylindrical device to move water from the low-lying Nile River up into the elevated dirt irrigation ditches. The farmers grew wheat and barley in the dry fields, requiring a constant supply of river water to maintain the crops. The lifting device consisted of a solid wooden center shaft measuring 8 feet long. A continuous wooden blade wrapped around this central pole at a precise angle, forming a spiral thread. The farmers enclosed this entire wooden spiral inside a hollow wooden cylinder made from wooden planks, sealed with pine pitch. The agricultural workers placed the bottom end of the wooden cylinder directly into the flowing water of the Nile River. They rested the top end of the heavy wooden tube on the dirt bank of the irrigation trench, angling the device at exactly 45 degrees. The workers stood on the muddy bank and turned a wooden crank handle attached to the top of the center shaft. The rotational motion spun the internal wooden spiral inside the stationary hollow casing. The bottom edge of the wooden thread scooped a specific volume of river water. As the workers turned the crank, the angled wooden blade pushed the water upward along the pitch-sealed interior walls. The rotational force applied by human muscles moved the heavy liquid mass against the direct downward pull of gravity. The river water spilled out the top opening and flowed into the dry dirt channels to water the wheat roots. James Lewis Pullman studied how this ancient rotational principle applied to solid loads. A threaded screw acts as a continuous inclined plane wrapped around a central cylinder. The physical distance between each wrap of the spiral thread is called the pitch. A smaller pitch creates a gentler incline on the shaft, requiring a lower amount of physical force to turn the cylinder while moving the load a shorter vertical distance. The spiral thread converts rotational motion into linear lifting force. The physical geometry of the inclined plane holds the lifted load in a stationary position when the rotational force ceases. The metal thread rests flat against the corresponding groove, locking the weight entirely in place through direct surface friction. Carpenters and farmers in 1831 used small wooden and iron screws to bind furniture joints and press crushed cider apples. James Lewis Pullman required massive load-bearing iron screws to lift entire houses. Blacksmiths forged threaded iron rods by heating raw wrought iron bars in coal-fired forges reaching 2,000 degrees Fahrenheit. The blacksmiths hammered the glowing red iron on steel anvils to form perfect cylinders measuring 3 inches in diameter and 2 feet long. The metal workers clamped the cooled iron cylinders into steel vises. They used hardened steel cutting tools called dies to carve continuous, deep spiral threads into the exterior surface of the iron shaft. The blacksmiths then cast heavy iron blocks with matching internal threads to serve as the stationary base, creating a complete jackscrew assembly. James Lewis Pullman acquired these heavy iron jackscrews forged by local metal workers. He tested the load-bearing capacity of the forged iron threads by placing heavy wooden pine beams directly on top of the vertical metal shafts. He applied oil rendered from animal fat to the iron threads to lubricate the metal-on-metal contact points between the shaft and the stationary base block. He gripped the iron shaft with a forged steel wrench, measuring 3 feet long. He applied horizontal force to the steel wrench and turned it in a complete circle. The continuous spiral thread pushed the heavy wooden beam upward exactly 1/4 of an inch. The iron threads supported the full weight of the pine beam after he released the steel wrench. James Lewis Pullman calculated the exact physical requirements to scale this lifting system. A standard 2-story wooden house with a footprint of 600 square feet weighed approximately 30,000 pounds. A single threaded iron jackscrew, measuring 3 inches in diameter, supported 3,000 pounds of vertical weight before the cast iron threads warped under the physical pressure. Distributing the 30,000 pounds evenly across 10 thick iron jackscrews allowed the metal threads to sustain the structural load safely. The carpenter spent the next 10 years developing a synchronized lifting system utilizing multiple heavy iron screws placed under the massive oak sills of residential structures. He designed interlocking wooden support blocks cut from oak timbers to hold the metal bases steady on the soft dirt. In the year 1841, James Lewis Pullman filed formal paperwork with the United States Patent Office to register his new machine utilizing these threaded metal jackscrews. In the spring of 1841, James Lewis Pullman submitted a formal application to the United States Patent Office, located in Washington, D.C. The application included detailed mechanical drawings sketched in black iron gall ink on heavy cotton paper. The drawings illustrated a large wooden frame combined with multiple iron screw jacks, turning simultaneously to lift a residential structure. Pullman submitted a miniature working wooden model of his lifting machine, fulfilling a strict legal requirement of the Federal Patent Office at that time. The Commissioner of Patents, Henry L. Ellsworth, oversaw the review of the mechanical submission. On August 19, 1841, the federal government granted patent number 2223 to James Lewis Pullman for his building moving apparatus. The official document described a system utilizing a series of threaded cast iron jackscrews combined with heavy wooden crossbeams. The physical patent papers contained the handwritten signatures of the patent examiners and the pressed red wax seal of the federal government. To operate the patented machine, workers excavated the packed dirt around the stone foundation of a wooden house using flat steel shovels with ash wood handles. The men dug shallow trenches measuring 3 feet wide and 2 feet deep along the entire perimeter of the dwelling. They leveled the bottom of these trenches by tamping the soil with heavy iron weights attached to wooden poles. The workers placed square wooden blocks cut from 12-inch thick white oak logs directly onto the flattened dirt. These dense oak blocks distributed the concentrated load of the iron machinery over a wider area of soil. The workers then set cast iron base plates weighing 50 pounds each on top of these oak blocks. Each heavy iron plate contained a threaded central hole measuring exactly 3 inches in diameter. The men inserted threaded solid iron screw shafts into these cast iron base plates. Before inserting the shafts, the workers applied rendered animal tallow to the exposed iron threads. This thick yellow fat reduced the metal-on-metal friction between the moving shaft and the stationary base. The workers positioned these jack screw assemblies every 8 feet along the exterior walls of the house. They placed heavy eastern white pine timber beams directly on top of the vertical iron shafts. The men pushed the flat upper surfaces of these pine beams flush against the underside of the house's original oak sills. The top of each iron screw shaft featured a square metal head with a circular horizontal hole passing completely through the center. A worker inserted a solid steel crowbar, measuring 3 feet long and weighing 15 pounds, into this circular hole. The worker stood in the dirt trench and pushed the steel bar horizontally, walking in a tight circle around the iron base. This continuous physical motion rotated the threaded screw shaft inside the stationary base plate. The angled iron threads pushed against the internal grooves of the base plate, forcing the solid iron shaft to move vertically upward. The spiral thread converted the horizontal walking energy of the worker into direct vertical lifting force, providing a massive mechanical advantage. A single, complete rotation of the steel crowbar raised the heavy pine timber, resting on top of the shaft, exactly 1/4 of an inch. A standard 30,000-pound wooden house required 10 of these iron jack screws, distributed evenly under the perimeter sills. 10 workers positioned themselves at the jack screw stations around the foundation. A foreman blew a brass whistle, signaling the men to push. Every worker pushed their steel bar exactly 1/4 of a full circle at the same exact time. The simultaneous rotation of the 10 metal threads lifted the entire 30,000-pound house 1/16 of an inch in a single, coordinated movement. The cast iron threads locked the massive weight in place the exact moment the workers stopped pushing the steel bars. The metal-on-metal friction of the inclined plane held the 15 tons of wood and plaster suspended entirely in the air. The house rose straight upward, separating from the original fieldstone foundation. The synchronized turning of the screws kept the wide pine floorboards perfectly level during the entire elevation process. The structural mortise and tenon joints held firm, maintaining the 90-degree angles of the wooden frame. The brittle white lime mortar inside the central brick heating chimney remained completely intact as the house ascended 12 inches into the air over the course of 3 hours. Once the workers elevated the house, they slid horizontal pine tracks and solid white oak rollers directly underneath the suspended pine sled beams. The workers rotated the iron screws in the reverse direction by pulling the steel crowbars backward. The house lowered at a rate of 1/16 of an inch per turn until the heavy oak sills rested completely on the smooth wooden cylinders. The crew then removed the vertical jack screws from the dirt trenches. They repositioned the same iron jack screws horizontally behind the house, placing the metal bases against heavy wooden stakes driven deep into the ground. The workers aligned the heads of the horizontal jack screws directly against the rear ends of the pine sled beams. The men turned the steel crowbars, forcing the iron screw shafts to push horizontally against the wooden carriage. The continuous mechanical pressure from the threaded screws propelled the structure across the log rollers at a steady rate of 1/4 of an inch per rotation. The steady mechanical pushing maintained a constant, even pressure on the wooden frame of the house. James Lewis Pullman applied this patented lifting and pushing method to residential structures and agricultural barns in Chautauqua County over the next 4 years. In 1845, the state of New York initiated a massive public works project to widen the water channels of the Erie Canal. The state legislature approved a budget of over $20 million to enlarge the canal prism to 70 feet wide and 7 feet deep. This expansion project required the removal of dozens of buildings situated within the new 70-foot boundary, prompting the Pullman family to move their entire operation east to the canal town of Albion, New York. In 1845, the state of New York directed civil engineers to expand the physical dimensions of the Erie Canal. The original water channel, completed in 1825, measured 40 feet wide at the surface and 4 feet deep. Thousands of manual laborers used forged iron pickaxes to break the hard clay banks and loaded the loose dirt into wooden horse-drawn carts. The construction crews excavated the dirt banks to widen the water surface to 70 feet. The workers dug the canal bed down to a new depth of 7 feet to accommodate heavier wooden freight barges. This physical expansion required the state government to seize strips of land measuring 15 feet wide along both parallel banks of the waterway. Commercial merchants had built wooden warehouses directly on the original dirt banks to load cargo onto passing boats. Farmers had erected timber-framed storage barns along the water edge to transfer heavy canvas sacks of harvested wheat onto the wooden vessels. Residential carpenters had constructed 2-story brick and wood homes within 20 feet of the original waterline. The new 70-foot canal width intersected the physical fieldstone foundations of these existing structures. The state engineers marked these specific buildings for immediate physical removal. James Lewis Pullman observed this massive public works project from his workshop in Brockton, New York. In 1845, he packed his cast-iron jack screws and white oak support beams into horse-drawn freight wagons. He relocated his wife and their 14-year-old son, George Mortimer Pullman, 90 miles northeast to the canal town of Albion, New York. Albion sat directly on the route of the Erie Canal in Orleans County. The town featured dozens of commercial structures standing directly in the path of the approaching canal excavation. Masons had built heavy brick grain storehouses resting on thick limestone foundations along the water edge. Carpenters had erected wooden storage sheds holding forged iron farming tools and heavy oak barrels of salted pork. The physical weight of these Albion structures ranged from 50 to 500 short tons. The New York state government issued public contracts to clear the designated canal zone. The state required the contractors to complete the relocations before the spring thaw filled the canal with melted ice. James Lewis Pullman submitted formal bids to the state engineers to relocate these heavy buildings intact to new plots of land. He presented his 1841 federal patent documents, demonstrating his threaded iron jackscrew lifting system. The state officials awarded him the relocation contracts, paying him directly from the $20 million enlargement budget. James Lewis Pullman hired local laborers in Albion to operate his heavy iron lifting machinery. The hired workers carried flat steel shovels with ash wood handles to the edge of the Erie Canal. They dug trenches measuring 3 feet wide directly into the wet clay surrounding the limestone foundations of the commercial warehouses. The canal water seeped into the freshly dug dirt trenches, carrying the distinct scent of green algae and wet river silt. The workers dropped flat, rough-sawn oak planks directly into the mud to create stable horizontal platforms for the heavy cast-iron base plates. The men placed cast-iron base plates, weighing 50 pounds each, onto the oak planks every 8 feet around the perimeter of the warehouse. They inserted solid iron shafts, measuring 3 inches in diameter, into the threaded circular holes of the base plates. The men hoisted thick eastern white pine beams, measuring 12 inches wide and 40 feet long, onto the flat metal tops of the vertical iron screws. The workers wedged the top surfaces of these pine sled beams directly under the heavy oak floor sills of the commercial warehouse. 14-year-old George Mortimer Pullman walked through the muddy dirt trenches alongside the adult laborers. The teenager carried a wooden bucket filled with yellow rendered animal tallow. He used a flat wooden stick to apply the thick, soft grease directly to the spiraling cast-iron threads of the vertical shafts. George watched the workers insert heavy steel crowbars into the square metal heads of the vertical screw shafts. The teenager carried a wooden measuring stick with 1-inch markings carved into the wood to verify the exact elevation height at each lifting station. The foreman sounded a brass whistle to coordinate the manual labor. The workers pushed the steel crowbars in a continuous horizontal circle around the iron base plates. The spiral iron threads turned through the heavy base plates, converting the circular motion into a direct vertical lift. The distributed weight of the 50-ton warehouse pressed down on the greased metal threads. The mechanical advantage of the inclined plane allowed a single worker pushing a crowbar to lift thousands of pounds of structural weight. The thick pine beams pressed upward against the original oak sills. The heavy warehouse structure separated from the limestone foundation with a loud cracking sound of snapping lime mortar. The building rose 1/4 of an inch above the stone blocks, with each full rotation of the steel bars. The men continued to push the steel bars, raising the heavy wooden warehouse 24 inches into the air. Once the structure reached the necessary 24-inch height, the crew placed continuous flat wooden tracks and solid white oak rollers beneath the suspended pine sled beams. The workers repositioned the iron jack screws horizontally behind the suspended structure. They braced the cast iron base plates against thick oak stakes driven 4 feet deep into the wet clay bank. The workers rotated the steel crowbars, forcing the threaded iron shafts to push horizontally against the rear ends of the pine carriage. The mechanical pressure forced the heavy building to roll slowly away from the canal bank at a rate of 1 inch per minute. As the structure rolled forward, the oak cylinders emerged from the rear of the pine sled. Workers picked up the heavy wooden rollers and carried them to the front of the tracks, maintaining continuous support beneath the rolling warehouse. The workers pushed the structures 50 feet back from the water edge, clearing the exact dimensions required for the approaching canal diggers. James Lewis Pullman repeated this exact extraction and relocation process on dozens of wooden and brick structures along the Albion Canal banks. Between 1845 and 1852, he continuously refined the placement of his wooden support grids, transferring this technical engineering knowledge directly to his son through daily physical labor under the elevated structures. Between 1845 and 1852, James Lewis Pullman operated his structural relocation business along the banks of the Erie Canal in Albion, New York. The wet clay of the canal bank compressed unevenly under the immense weight of the relocated commercial structures. To stabilize the heavy brick and wood buildings on the soft earth, James Lewis Pullman utilized a physical support system called box cribbing. Workers cut square timbers from eastern hemlock and white oak trees, harvested from the nearby New York forests. These dense wooden beams measured exactly 6 inches wide, 6 inches thick and 4 feet long. The laborers carried these heavy wooden beams, weighing roughly 40 pounds each, down into the excavated dirt trenches beneath the buildings. They laid 2 parallel oak timbers directly onto the flat mud, spacing the parallel beams exactly 3 feet apart. The men placed 2 more square timbers on top of the first pair, turning the new beams at a precise 90-degree angle to create a hollow square footprint. The workers continued stacking these interlocking timbers in alternating directions, building hollow wooden towers, layer by layer. The intersecting corners of the square beams transferred the downward physical weight directly into the flat soil below. The open center of the wooden tower reduced the total volume of wood required by 50%, while maintaining the structural load capacity of a solid wooden column. The threaded cast-iron shafts of the jack screws possessed a maximum vertical reach of exactly 14 inches. To lift a warehouse higher than the physical length of the iron screw, the workers combined the metal lifting machines with the wooden box cribs. They placed the cast-iron base plates directly on top of the completed wooden towers. The men inserted the threaded iron shafts into the base plates. They pushed the heavy steel crowbars in a horizontal circle, driving the metal threads upward against the flat bottom of the pine sled beams. The commercial building rose 14 inches into the air, reaching the maximum physical limit of the metal jack screw. The building hung suspended above the dirt trenches, supported entirely by the iron threads. The laborers rapidly built a second set of wooden box cribs directly beneath the suspended pine carriage. They stacked the interlocking hemlock timbers until the top beam touched the flat underside of the wooden sled. The men turned the steel crowbars in the reverse direction, lowering the vertical iron shafts down into the base plates. The full weight of the massive warehouse transferred from the metal jack screws directly onto the newly constructed wooden towers. The intersecting hemlock beams groaned audibly as the wood fibers compressed under the 50-ton structural load. With the building resting firmly on the interlocking wood, the workers removed the iron jack screws from their original positions. They added 2 more layers of intersecting timbers to the first set of wooden towers, increasing their physical height by exactly 12 inches. The laborers hoisted the 50-pound cast-iron base plates back on top of these taller wooden columns. They reset the vertical iron shafts under the pine carriage and turned the steel crowbars again, lifting the structure another 14 inches into the air. Teenage George Mortimer Pullman spent 7 years working beneath these suspended commercial buildings in Albion. He stacked the rough hemlock timbers by hand, aligning the 90-degree corners to maintain the exact vertical center of gravity. The rough bark of the cut wood pressed into his palms as he built the interlocking frames in the damp trenches. He observed his father measure the exact vertical height of each wooden tower using a heavy lead plumb bob attached to a cotton string. George carried the heavy cast-iron base plates through the mud, positioning the metal blocks squarely on top of the wooden columns. He coated the cast-iron threads with rendered animal fat, wiping the yellow grease deep into the spiral metal grooves. The thick layer of grease prevented the metal from binding or sparking under the immense physical pressure of the building. The grease smelled of roasted meat and held small grains of loose sand from the trench walls. He watched the massive brick and wood structures rise straight into the air above his head, inch by inch, resting entirely on the temporary wooden foundations. The workers repeated this exact lifting and resetting process dozens of times for a single building. The hollow wooden towers grew to heights of 6 to 10 feet above the muddy canal banks. The continuous stacking of the box cribs allowed the crew to elevate structures to any required height, limited only by the total number of wooden timbers available on the work site. The combination of the mechanical iron screw and the interlocking wooden crib formed a complete, scalable elevation system. James Lewis Pullman applied this specific combination of iron and wood to complete his state contracts along the Erie Canal over a period of 7 years. The physical requirements of the outdoor manual labor placed him constantly in the wet dirt trenches. He exposed his body to the freezing wind and cold, damp soil of western New York during the long winter relocations. In the autumn of 1853, James Lewis Pullman developed a severe physical illness in the town of Albion. He died shortly after contracting the illness, leaving the heavy cast-iron jackscrews, the white oak timbers, and the active state relocation contracts in his workshop. The death of the patriarch required 22-year-old George to step forward and take physical possession of the family mechanical lifting enterprise. In the late autumn of 1853, James Lewis Pullman died in the town of Albion, New York. His death transferred the physical ownership of the structural relocation business directly to his 22-year-old son, George Mortimer Pullman. George walked into his father's wooden workshop, situated on the banks of the Erie Canal. He inventoried the mechanical lifting equipment, stored directly on the packed dirt floor. He counted 200 cast-iron jackscrews, 50 forged steel crowbars, and 400 white oak timber blocks. The threaded iron shafts carried the yellow stains of rendered animal fat applied during years of canal work. George placed his bare hands on the cold forged metal tools, claiming legal possession of the family enterprise. He reviewed the original 1841 United States patent documents printed on heavy cotton paper. The ink drawings detailed the exact spacing and rotational synchronization required to lift heavy buildings. In the spring of 1854, civil engineers from the state of New York identified 20 commercial and residential structures obstructing the newly widened path of the Erie Canal. The state government issued a public request for contractors to clear the designated 70-foot water channel. George Pullman submitted a formal written bid to relocate all 20 buildings to new plots of land. The state officials awarded the government contract to the 22-year-old operator. George hired 30 local laborers from the surrounding Orleans County farms. He agreed to pay each worker a standard daily wage of $1.25. He distributed the weekly wages using USA minted silver dollar and quarter-dollar coins. He instructed the men to load the heavy cast-iron jackscrews and the white oak blocks into horse-drawn wooden freight wagons. Teams of draft horses pulled the heavy equipment along the dirt towpath beside the flowing canal water. The crew transported the mechanical equipment to the first designated structure listed on the state contract. The target building consisted of a 2-story wooden warehouse resting on a fieldstone foundation 20 feet from the canal water. The entire timber structure weighed approximately 40 short tons. George directed the 30 laborers to dig 3-foot-wide trenches in the wet clay surrounding the base of the structure. The men used flat steel shovels to remove the damp soil, exposing the bottom edge of the fieldstone foundation. George measured the exact exterior perimeter of the warehouse using a 50-foot canvas tape measure. He marked the specific locations for the iron jackscrews exactly 8 feet apart along the exposed wooden floor sills. The workers laid flat oak planks into the bottom of the mud trenches to establish a level bearing surface for the metal machines. The laborers constructed the hollow wooden box cribs by stacking 6-inch hemlock timbers at 90-degree angles. They placed the 50-pound cast-iron base plates directly on top of the stacked wooden towers. George walked through the dirt trenches and inspected the vertical alignment of each iron screw shaft. He held a brass plumb bob suspended by a cotton string next to the metal threads to verify the exact perpendicular angle to the ground. The men hoisted 40-foot eastern white pine beams onto the flat metal tops of the vertical iron screws. George ordered the workers to wedge the top surfaces of the pine timbers tightly against the original oak floor sills of the warehouse. He handed heavy steel crowbars to 10 selected workers standing in the trenches. The men inserted the 3-foot metal bars into the square heads of the vertical iron jack screws. George stood 20 feet away from the structure and blew a brass whistle. At the exact sound of the whistle, the 10 men pushed their steel bars simultaneously in a circular motion. The threaded iron shafts rotated inside the stationary cast-iron base plates, pushing the heavy pine sled beams upward. The 2-story wooden warehouse separated from the fieldstone foundation, rising 1/4 of an inch into the air. George blew the whistle a second time, and the men completed another identical rotation. The team repeated this synchronized manual labor throughout the afternoon, elevating the 40-ton structure exactly 24 inches above the original fieldstone base. The crew placed the solid white oak rollers and flat wooden tracks directly beneath the suspended pine carriage. They repositioned the iron jack screws horizontally behind the warehouse, anchoring the cast-iron base plates against thick wooden oak stakes driven 4 feet deep into the earth. The men turned the steel crowbars, pushing the structure horizontally away from the canal bank. The solid oak rollers rotated under the heavy pine sled beams, crushing the spring grass on the adjacent plot of land. George measured the physical distance traveled using his canvas tape, halting the crew when the warehouse reached exactly 50 feet from the new canal boundary. The masons constructed a new fieldstone foundation beneath the suspended building. The workers reversed the vertical jack screws and lowered the wooden sills onto the fresh mortar. George Pullman executed this exact physical process on all 20 structures listed in the 1854 state contract. His crew relocated heavy brick storehouses, wooden timber barns, and plastered residential homes over a period of 8 months. The hired laborers turned the heavy steel crowbars through the hot summer weeks and into the cold autumn rain. George maintained the precise synchronization of the metal jack screws, preserving the structural integrity of the plaster walls and glass windows. The original white lime mortar in the relocated brick chimneys held completely firm. The wide pine floorboards remained perfectly level after reaching their new fieldstone foundations. The New York State Civil Engineers inspected the cleared 70-foot canal zone. They verified the safe relocation of the 20 buildings and approved the final payment to George Pullman. The state government issued paper bank drafts to George, increasing his total financial capital to roughly $6,000. The Erie Canal widening project in Orleans County neared completion, shifting the local demand for manual labor toward agricultural harvesting. George packed his iron jack screws into wooden crates to seek new commercial contracts in western cities. Hundreds of miles to the west, the growing city of Chicago, Illinois, occupied a flat, muddy plain located squarely on the western shore of Lake Michigan. The elevation of the Chicago area measured only a few feet higher than the water level of the adjacent lake. The flat topography trapped standing water permanently in the unpaved dirt streets and around the physical foundations of the expanding commercial district. In the spring of 1854, the municipal boundaries of Chicago, Illinois, enclosed approximately 18 square miles of flat, marshy land. The city grid sat exactly on the western shoreline of Lake Michigan, situated directly at the mouth of the slow-moving Chicago River. The natural topography of this landform sat an average of 3 feet above the surface level of the adjacent lake. The underlying soil profile of the region consisted of a thick layer of dense blue clay topped with a shallow layer of black marsh soil. This compressed clay substrate held an extremely low water percolation rate, preventing surface water from draining downward into the deeper earth. During the frequent rainstorms of 1854, the heavy precipitation fell directly onto the flat topography of the unpaved city streets. The flat grading and the dense clay trapped the rainwater entirely on the surface of the ground. The local water table sat just 12 inches below the topsoil, keeping the earth permanently saturated with moisture. The standing water pooled rapidly in the dirt streets of the central commercial district. Heavy wooden freight wagons with iron-rimmed wheels rolled continuously over these dirt roads, carrying loads of harvested wheat and cut white pine lumber. The heavily loaded wagons weighed over 4,000 pounds each. The narrow iron wheel rims sliced into the wet clay, crushing the saturated soil into deep trenches of liquid mud. The iron wheels sank up to 24 inches deep into the wet clay, trapping the horse-drawn wagons entirely in the streets. The draft horses struggled to pull the heavy freight through the viscous sludge, sinking up to their knees in the dark mud. Pedestrians attempting to cross the commercial intersections stepped directly into cold brown water mixed with horse manure and displaced soil. The municipal government of Chicago laid raw pine planks horizontally across the mud to create temporary wooden sidewalks for the foot traffic. Workers nailed 2-inch thick pine boards to wooden sleepers, resting directly on the wet earth. The standing water frequently overflowed and submerged these wooden planks, leaving the pedestrian walkways entirely underwater during the heavy spring rains. Builders constructed hundreds of new timber-framed structures and heavy brick commercial blocks directly on top of this saturated soil along Lake Street and Water Street. Carpenters laid heavy oak sill beams directly onto the wet black earth to serve as the foundations for the wooden residential houses. The extreme physical weight of the timber frames compressed the soft clay, causing the oak sills to sink several inches down into the mud. The ground floor pine planks absorbed the standing surface water through direct physical contact. The damp wood expanded and warped under the moisture, cracking the interior plaster walls of the residential dwellings. Masons building the heavy brick commercial warehouses dug shallow trenches into the mud to lay their fieldstone foundations. The high groundwater seeped instantly into these excavated dirt trenches. The fast-rising water forced the masons to drop the heavy limestone blocks directly into standing pools of dark water. The completed multi-story brick buildings pressed down on the soft clay with thousands of tons of physical force. The wet earth yielded unevenly under the corners of these massive brick structures, causing the entire buildings to tilt slightly out of vertical alignment. The uneven settling cracked the white lime mortar joints connecting the red clay bricks. The stagnant water surrounding the foundations carried the physical waste of a rapidly expanding human and animal population. Chicago held a census population of nearly 60,000 human residents by the year 1854. The city infrastructure contained no underground sewer pipes to remove the daily accumulation of human waste and commercial refuse. Residents dug shallow privy pits into the dirt backyards behind their wooden homes to hold the raw sewage. The high water table flooded these shallow holes, pushing the raw human waste directly back up to the ground surface. The dark surface water mixed with the overflowing waste and flowed slowly into the unpaved streets. Commercial slaughterhouses operated along the banks of the South Branch of the Chicago River, butchering thousands of pigs and cattle each month. The workers dumped the animal blood bone fragments, and discarded offal directly into the slow-moving river water. The flat topography provided a water current of less than 1 mile per hour, failing to flush the heavy biological waste out into the deeper waters of Lake Michigan. The dirty water sat stagnant around the wooden sills and brick foundations for weeks at a time. The stagnant pools of brown water rested undisturbed in the dirt gutters, releasing the strong smell of sulfur and decaying organic matter into the air. As the spring of 1854 transitioned into summer, the ambient air temperature rose above 80 degrees Fahrenheit. The direct sunlight heated the shallow, stagnant pools of contaminated water resting in the streets and under the floorboards of the homes. The warm, nutrient-rich water created an optimal physical environment for the rapid reproduction of microscopic pathogens. The residents of Chicago drew a large portion of their daily drinking water from shallow wells dug directly into this contaminated topsoil. Other residents received their water from the Chicago Hydraulic Company, a private commercial enterprise. The company operated a 25-horsepower steam engine on the shoreline of Lake Michigan. The cast-iron steam pump drew water from the lake and pushed it into a raised wooden reservoir. The water flowed by gravity from the reservoir through a network of hollowed-out cedar logs buried under the muddy streets. The wooden intake pipe for this steam pump extended only 150 feet into the shallow waters of Lake Michigan. The intake pipe sat just south of the mouth of the Chicago River, exactly where the slow current deposited the animal waste and raw sewage into the lake. The cast-iron steam engine pumped this contaminated lake water directly into the hollow cedar logs leading to the residential houses. The contaminated surface water also drained slowly through the sandy topsoil into the private shallow drinking wells, mixing the raw waste directly with the household well water. By the summer months of 1854, the residents of the city began ingesting this pathogenic water daily, drinking the liquid directly from their metal tin cups and setting the exact physical conditions for a severe cholera epidemic. In the summer months of 1854, the average daily temperature in Chicago, Illinois, climbed above 85 degrees Fahrenheit. The standing pools of surface water in the unpaved dirt streets warmed under the direct summer sunlight. Microscopic cholera bacteria multiplied rapidly inside these stagnant puddles of contaminated water. Residents drew daily drinking water from their shallow backyard wells and from the hollowed-out cedar logs installed by the Chicago Hydraulic Company. The citizens transferred this water into tin cups and ceramic mugs, ingesting the live cholera bacteria directly into their digestive systems. The bacteria traveled through the human stomach and colonized the small intestine. The microscopic organisms released a specific chemical toxin that disrupted the normal function of the intestinal lining. This biological disruption caused the human body to expel massive quantities of fluid and sodium directly into the digestive tract. The infected residents lost up to 1 quart of water per hour through severe digestive purging. The rapid loss of internal fluids dropped the total volume of blood circulating in the human body. As the overall blood volume decreased, the human heart pumped faster to maintain physical circulation, pushing the pulse rate above 120 beats per minute. The severe loss of electrolytes caused the skeletal muscles in the legs and arms to contract in sustained physical spasms. The skin of the infected individuals lost its physical elasticity and turned a pale shade of blue due to the lack of oxygenated blood in the capillaries. The severe dehydration halted the function of the human kidneys, ceasing the production of urine. Medical doctors in Chicago lacked intravenous fluid treatments in 1854. The physicians prescribed small doses of laudanum, a liquid mixture of alcohol and opium, to ease the physical muscle cramps. The rapid internal fluid loss caused death from severe dehydration within 12 to 24 hours of the first physical symptoms. During the months of July and August 1854, the cholera epidemic killed roughly 3,300 residents of Chicago. This mortality number represented exactly 5.5% of the entire city population of 60,000 people. Carpenters worked continuous 10-hour shifts, cutting white pine boards with steel handsaws to construct rectangular wooden coffins. The carpenters joined the pine boards using forged iron nails and heavy steel hammers. Horse-drawn wooden wagons transported the assembled pine coffins to the city cemetery, located on the northern edge of the municipal boundaries directly adjacent to the shoreline of Lake Michigan. Grave diggers used flat steel shovels with ash wood handles to excavate 6-foot-deep trenches in the sandy soil near the lake. The high water table caused the freshly dug graves to fill immediately with 2 feet of groundwater. The grave diggers dropped the heavy pine coffins directly into the standing water at the bottom of the burial trenches. The men shoveled the wet sand back into the holes to cover the wooden boxes. The dense concentration of shallow burials near the lake shore contaminated the surrounding groundwater with additional biological material. Thousands of healthy residents packed their physical clothing into wooden trunks and leather bags to flee the epidemic. They boarded steam-powered locomotives at the Galena and Chicago Union Railroad depot, leaving the city for the surrounding agricultural towns in the Illinois countryside. The sudden departure of the population halted commercial trading operations along the Chicago River. The brick grain warehouses sat empty, and the heavy wooden freight barges remained tied to the oak docks with thick hemp ropes. The severe loss of human life and the disruption of commercial trade forced the Common Council of Chicago to convene an emergency legislative session. The local aldermen met inside the brick municipal courthouse situated in the center of the city square. The elected officials sat at heavy oak tables and reviewed the public mortality records recorded in paper ledgers using black iron gall ink. The council members voted unanimously by raising their hands to form a special committee to address the standing water in the city streets. The committee hired land surveyors to measure the exact elevation of the commercial district in relation to the water level of Lake Michigan. The surveyors used brass transit levels mounted on wooden tripods and carried wooden measuring rods marked with 1-inch increments. The surveying crew recorded their physical measurements in leather-bound field books using graphite pencils. The surveyors presented their recorded numbers directly to the Common Council. The physical measurements proved the central city streets sat only 3 to 4 feet above the surface of Lake Michigan. A gravity-fed underground sewer pipe requires a continuous downward slope of at least 1 inch per 100 feet to move heavy wastewater effectively. The dense blue clay beneath Chicago sat too low to provide the necessary physical slope for an underground drainage system. Any ceramic pipe, buried 6 feet under the dirt streets, sat completely below the water level of Lake Michigan, causing the lake water to flow backward into the open pipes. The physical geometry of the land required the installation of an above-ground drainage system to achieve the necessary downward slope. The aldermen of the Common Council recognized the necessity of hiring an experienced hydraulic engineer to design this massive infrastructure project. The committee sent official letters via the USA Postal Service to the East Coast, seeking an expert in municipal water systems. In 1855, the council contacted Ellis S. Chesbro, a civil engineer residing in Massachusetts. Chesbro previously designed the gravity-fed brick aqueducts for the Boston Water Works. The Chicago alderman offered Chesbro the newly created position of chief engineer for the Chicago Board of Sewerage Commissioners to draft a comprehensive plan for a citywide drainage system. In 1855, Ellis S. Chesbro accepted the position of chief engineer for the Chicago Board of Sewerage Commissioners. He relocated from Boston, Massachusetts, to the muddy flatlands of Chicago, Illinois. In 1856, Chesbro presented a comprehensive physical plan to the Common Council to construct a gravity-fed municipal sewer network. The elected aldermen voted to approve the infrastructure project and allocated municipal funds to begin construction immediately. Chesbro surveyed the dense blue clay and the high water table. The standing groundwater sat exactly 12 inches below the surface of the unpaved streets. This shallow water level forced the engineering team to design an entirely above-ground drainage system. The workers placed the new sewer pipes directly on top of the existing dirt roads. Chesbro designed the main sewer lines using circular brick conduits measuring up to 6 feet in diameter. Local masons constructed these large tubes by stacking fired red clay bricks in a continuous arch over a temporary wooden centering frame. The masons bound the clay bricks together using waterproof hydraulic cement sourced from Utica, Illinois. This specific cement cured rapidly in the damp air, creating a solid, sealed cylinder resting directly on the flat mud. For the smaller branch sewers extending into the residential neighborhoods, the workers laid vitrified clay pipes measuring 12 inches in diameter. The manufacturing process of vitrified clay involved a high-heat firing technique that melted the outer surface of the clay into a smooth, waterproof glass. The laborers connected these smaller clay pipes to the large brick mains, forming a continuous network across the 18-square-mile city grid. The engineers pitched every pipe at a precise downward angle, dropping exactly 1 inch for every 100 feet of linear distance. This continuous physical slope directed the heavy wastewater toward the Chicago River, utilizing gravity to move the fluid mass. Placing the large brick conduits directly on the existing roads created massive physical obstacles in the center of the commercial thoroughfares. The 6-foot-tall brick tubes blocked horse-drawn wagons from crossing the intersections. To restore the function of the roadways, Chesbro ordered contractors to cover the entire sewer network with imported soil. The Common Council hired dredging barges to excavate the bottom of the Chicago River and the nearby Illinois and Michigan Canal. Steam-powered dredges, equipped with iron buckets, scooped thick, wet mud and heavy river sand from the channel floors. Laborers loaded this excavated river silt into horse-drawn wooden carts. The drivers transported the wet soil to the commercial district and dumped the heavy earth directly over the exposed brick and clay sewer pipes. The freshly dredged river mud carried the strong scent of sulfur and wet clay into the city center. The workers used flat iron shovels and heavy wooden tampers to pack the wet river sand tightly around the curved masonry. The volume of the required soil raised the entire physical grade of the city streets by an average of 6 feet. In some central sections near the river, the new street level rose as high as 8 feet above the original dirt grade. Contractors laid new cedar paving blocks directly on top of the freshly packed earth. The workers cut the cedar logs into hexagonal blocks, measuring 6 inches tall. They placed these wooden blocks side by side on the raised soil, creating a continuous paved surface for the heavy freight wagons. The draft horses pulled their wagons across the new cedar streets, rolling 6 feet higher than the old muddy pathways. This massive elevation of the public roadways created a severe discrepancy with the existing private buildings lining the streets. The new 6-foot soil embankments pressed directly against the first-floor wooden walls of the warehouses and homes. Property owners constructed thick pine retaining walls just inches from their front doors to hold back the heavy, wet soil. The newly elevated street surface sat completely flush with the second-story windows of the surrounding structures. Pedestrians walking on the new cedar streets looked directly down into the ground-floor entrances of the local businesses. To enter a shop, customers stepped off the raised roadway and walked down steep wooden staircases built into dark, recessed trenches. The original ground floors of these buildings transformed instantly into subterranean cellars, trapping damp air and restricting the entry of natural sunlight. Shop owners lit whale oil lamps during the day to illuminate their newly darkened merchandise rooms. The steep pine stairs, connecting the new high streets to the old low doorways, accumulated rainwater and slick mud during storms, causing pedestrians to slip on the wet wood. The municipal government maintained the new elevated street grade, requiring the property owners to adapt their private structures to the new height. The residents of Chicago faced a massive physical problem requiring a large-scale mechanical solution. To reconnect their doorways to the elevated public sidewalks, the building owners needed to physically lift thousands of heavy masonry and timber structures straight up into the air. The news of this massive municipal elevation project traveled east along the railway telegraph lines, reaching the town of Albion, New York. In 1857, 26-year-old George Mortimer Pullman packed his heavy cast-iron jackscrews into wooden railway freight cars and purchased a train ticket bound for the expanding city of Chicago. In 1857, George Mortimer Pullman arrived at the Galena and Chicago Union Railroad Depot in Chicago, Illinois. He directed railway workers to unload his wooden crates filled with 200 cast-iron jackscrews onto the wooden platform. The workers placed the heavy crates onto horse-drawn wagons resting on the newly elevated cedar block streets. These new wooden paving blocks sat exactly 6 feet higher than the original dirt ground level. Pullman opened a structural lifting business to elevate the existing residential and commercial buildings to meet this new 6-foot grade. He rented a physical workshop in the commercial district and stored his heavy iron lifting machines directly on the wide pine floorboards. He walked along the raised cedar sidewalks and inspected the sunken wooden structures lining the avenues. Property owners had built steep pine staircases leading down from the new streets into the original front doors of their homes. Rainwater flowed off the raised cedar blocks and poured directly into the recessed dirt trenches surrounding these ground floor entrances. The standing water rotted the white oak sills of the wooden houses, releasing the smell of decaying wood fiber and damp mold into the air. Pullman secured commercial contracts from these property owners to raise their wooden buildings up to the new street level. He hired local Chicago laborers and paid them a daily wage using USA minted silver coins. The crew loaded the cast-iron base plates and heavy steel crowbars into wagons and drove them to the residential neighborhoods. The workers descended the wooden stairs into the damp, 6-foot-deep trenches surrounding the houses. They used flat steel shovels to level the wet black mud at the base of the original fieldstone foundations. The saturated clay of the Chicago region held less weight per square foot than the soil in New York. The workers laid wide planks of eastern white pine directly onto the wet earth to distribute the massive structural loads. The men stacked square hemlock timbers on top of the flat planks, building hollow wooden box cribs at 8-foot intervals around the perimeter of the structure. The rough hemlock bark shed small flakes of wood into the standing water as the men aligned the 90-degree corners. The laborers placed the 50-pound cast-iron base plates on top of the wooden towers and inserted the threaded iron shafts. They applied thick yellow animal tallow to the metal threads to lubricate the lifting mechanisms. The workers hoisted 40-foot pine sled beams onto the flat metal tops of the vertical screws, wedging the wood tightly against the original oak sills of the house. A standard 2-story wooden home of this era measured 20 feet wide by 40 feet long, carrying a total structural weight of roughly 50 short tons. 10 men stood in the dark trenches, holding steel crowbars, measuring 3 feet long and weighing 15 pounds. At the sound of a brass whistle, the workers pushed the solid steel bars in a continuous horizontal circle. The metal threads of the jack screws turned inside the cast-iron base plates, converting the horizontal motion into direct vertical force. The wooden house separated from its fieldstone foundation with a loud crack of breaking mortar. The structure rose exactly 1/4 of an inch with each full rotation of the steel bars. The men continued walking in circles, turning the heavy steel crowbars and lifting the 50-ton wooden building 72 inches into the air. The physical exertion caused the men to sweat in the humid summer air as they maintained the steady rotational pace. With the house suspended 6 feet above the old ground level, local masons arrived at the site, carrying fired red clay bricks and heavy wooden buckets of wet lime mortar. The masons built new foundation walls directly underneath the suspended oak sills. They stacked the red bricks course by course, building a solid 6-foot wall extending from the old mud up to the newly elevated cedar street. The masons laid over 10,000 fired clay bricks to construct the new 6-foot-tall foundation walls around the entire perimeter of the home. The wet lime mortar released a sharp, alkaline scent into the confined air of the dirt trenches. The workers reversed the rotation of the steel crowbars, lowering the wooden house exactly onto the wet mortar of the new brick foundation. The front door of the house now opened directly onto the elevated cedar sidewalk. The residents walked straight out of their homes onto the public street, leaving the dark dirt trenches beneath them. The newly constructed brick foundation sealed the damp earth underneath the house, creating a dry cellar space enclosed by heavy masonry. Over the course of 1857, Pullman and his crew lifted dozens of these timber-framed residential homes along the expanding city grid. The physical process of lifting a wooden frame building relied on the natural flexibility of the pine and oak joints. The wooden mortise and tenon connections bent slightly under the mechanical pressure, absorbing the minor variations in the lifting speed between the different jack screws. Chicago contained hundreds of massive commercial structures built entirely from fired clay brick and cut limestone. A multi-story masonry building possessed absolute structural rigidity and weighed over 700 tons. The brittle lime mortar connecting the heavy bricks fractured and split the clay walls immediately if workers lifted one section of the building slightly faster than another section. To elevate these massive stone and brick warehouses, engineers required a perfectly synchronized lifting system utilizing hundreds of jack screws simultaneously. In January 1858, an engineer named James Brown secured a commercial contract to attempt the first complete elevation of a large masonry building situated at the northeast corner of Randolph Street and Dearborn Street. In January 1858, an engineer named James Brown executed the first complete physical elevation of a large masonry building in Chicago, Illinois. The structure stood on the northeast corner of Randolph Street and Dearborn Street in the Central Commercial District. Masons originally constructed this four-story commercial building using locally fired red clay bricks and rigid white lime mortar. The rectangular building measured exactly 70 feet long and 40 feet wide. The exterior walls contained multiple rows of double-hung wooden window frames fitted with flat glass panes. The complete physical structure held a total calculated weight of 750 short tons. The original ground floor of this heavy brick block sat entirely below the newly elevated cedar block streets. Rainwater and melted snow flowed off the raised roadway and pooled directly against the lower brick walls. James Brown secured the contract from the property owners to raise the entire 750-ton structure to meet the new street level. He hired 200 local manual laborers to perform the physical work. In the first week of January 1858, the ambient air temperature in Chicago dropped to 15 degrees Fahrenheit. Wind blowing from the frozen surface of Lake Michigan moved through the city streets at 20 miles per hour. The laborers wore thick wool coats and heavy leather work gloves to protect their skin from the freezing air. The workers carried flat steel shovels and forged iron pickaxes to the base of the brick building. The wet clay surrounding the foundation had frozen into a solid crust, measuring 6 inches deep. The men swung the heavy iron pickaxes, driving the sharp metal points deep into the frozen earth. The physical impacts shattered the hardened clay into sharp fragments of ice and dirt. The workers shoveled the broken soil into wooden wheelbarrows and rolled the debris away from the building. They dug continuous trenches, measuring 4 feet wide and 6 feet deep, along the entire 70-foot perimeter of the masonry walls. Inside the excavated dirt trenches, the laborers laid flat planks of eastern white pine directly onto the exposed soil. They stacked 6-inch square hemlock timbers on top of the pine planks to build hollow wooden box cribs. The dense hemlock wood provided a stable horizontal base for the metal lifting machines. The workers carried 200 cast-iron base plates down into the trenches, placing one metal plate every 3 feet along the wooden towers. The men inserted threaded solid iron shafts measuring 3 inches in diameter into each base plate. They used flat wooden sticks to apply thick yellow animal tallow directly to the spiraling metal threads. The cold winter air hardened the animal grease instantly, forming a solid lubricating layer on the cold iron. James Brown directed the workers to slide massive eastern white pine timbers directly underneath the brick walls. Masons used heavy iron mallets and steel chisels to cut square holes through the lowest courses of the existing brickwork. The workers inserted thick horizontal oak beams through these holes, resting the ends of the oak beams on the flat tops of the vertical jack screws. The massive structural weight of the building transferred directly from the original fieldstone foundation onto the 200 iron threads. James Brown stationed one laborer at each of the 200 jack screw positions. The men stood inside the freezing dirt trenches, holding solid forged steel crowbars. Each steel bar measured 3 feet long and weighed 15 pounds. James Brown stood on the elevated cedar street, holding a brass whistle. He blew the whistle, sending a sharp, high-pitched tone echoing off the surrounding brick facades. At the exact sound of the whistle, the 200 laborers pushed their steel crowbars in a horizontal arc. The synchronized physical motion turned the 200 iron threads exactly 1/4 of a full rotation. The metal threads pushed upward through the stationary cast-iron base plates. The simultaneous mechanical force lifted the entire 70-foot brick building 1/16 of an inch into the air. The heavy brick block separated from its original foundation with a sharp cracking sound as the old lime mortar fractured. James Brown blew the brass whistle a second time. The 200 men completed another synchronized quarter turn with the steel bars. The men maintained this steady rhythm, lifting the building precisely 1 inch per hour. The perfect synchronization of the 200 metal jack screws maintained a perfectly flat horizontal plane along the entire length of the heavy pine support beams. The uniform vertical lift distributed the 750 tons of physical weight evenly across the 200 metal machines. The rigid lime mortar connecting the thousands of red clay bricks remained entirely intact. The flat glass panes inside the wooden window frames maintained their solid physical structure. The interior plastered walls retained their smooth, continuous physical surfaces as the building rose into the winter air. The laborers turned the steel crowbars until the iron jack screws reached their maximum vertical extension of 14 inches. The crew constructed a second layer of wooden box cribs directly beneath the suspended pine timbers. They lowered the metal screws, transferred the weight to the new wood, and repositioned the iron jack screws on top of the taller cribbing. The crew repeated this lifting and resetting sequence continuously over the course of the week. They elevated the 4-story brick building a total distance of 6 feet and 2 inches above the original dirt level. Local masons entered the trenches, carrying rectangular red clay bricks and wooden buckets of fresh lime mortar. They stacked the bricks in overlapping courses to build a new permanent foundation wall, measuring exactly 74 inches tall. The wet mortar, cured in the freezing air, hardening into a solid calcium carbonate bond. The workers reversed the rotation of the jack screws, lowering the 750 tons of structural weight directly onto the freshly built masonry walls. The ground floor entrances of the commercial building now sat perfectly flush with the elevated cedar block street. The successful intact elevation of the Randolph Street building generated an immediate demand for large-scale masonry lifting across the city. In 1859, George Pullman formed a 3-person engineering partnership named Ely, Smith and Pullman to secure these massive new municipal contracts. In 1859, George Mortimer Pullman formed a commercial engineering firm in Chicago, Illinois. He partnered with 2 other men to create a 3-person enterprise named Ely, Smith and Pullman. The firm established a physical office in the Central Commercial District to secure contracts directly from local property owners. The municipal government of Chicago had recently covered the existing sewer pipes with dredged river mud, raising the cedar block streets by 6 feet. Property owners hired Ely, Smith and Pullman to lift their heavy masonry and timber buildings up to this new elevated street grade. The partnership combined their physical equipment, gathering hundreds of threaded cast iron jack screws and thousands of eastern hemlock timbers. The 3 men managed multiple relocation work sites across the Chicago grid simultaneously. George Pullman walked between the different commercial properties along Lake Street and South Water Street. He carried a heavy leather-bound notebook and a graphite pencil to calculate the specific structural weight of each brick building. A standard 3-story brick commercial block, built in 1859, contained roughly 130,000 fired red clay bricks. Each individual clay brick weighed 4½ pounds, bringing the total masonry weight to over 580,000 pounds. Pullman added the weight of the thick oak floor joists, the wide pine floorboards, and the slate roof shingles, calculating a total structural weight of roughly 600 short tons per building. The firm hired hundreds of local laborers and paid them $1.25 per day using USA minted silver coins. The workers carried flat steel shovels with ashwood handles to the edge of the brick buildings. They dug 6-foot-deep trenches around the entire perimeter of the structures. The muddy water of the Lake Michigan floodplain seeped directly into the freshly dug dirt. The laborers placed wide planks of white oak onto the wet clay to create a flat, load-bearing surface. They stacked square hemlock timbers measuring 6 inches thick into hollow wooden box cribs on top of these oak planks. Heavy masonry walls require continuous structural support to prevent the brittle lime mortar from cracking under physical stress. The firm spaced the wooden box cribs exactly 2 feet apart along the entire length of the brick foundation. The men hoisted 50-pound cast-iron base plates onto the flat tops of the wooden towers. They inserted threaded iron shafts measuring 3 inches in diameter into the circular holes of the base plates. The laborers coated the spiraling metal threads with yellow animal tallow. The thick grease reduced the metal-on-metal friction as the heavy iron parts moved against one another. Masons cut square holes through the red clay bricks at the base of the walls using forged steel chisels and heavy iron mallets. The laborers inserted thick white oak beams through these freshly cut holes. They rested the solid wood directly on the flat metal tops of the vertical jack screws. The entire structural weight of the 600-ton brick building transferred downward onto the iron threads. Ely, Smith, and Pullman employed over 100 men at a single building site to operate the lifting machines. The laborers stood in the damp dirt trenches holding solid forged steel crowbars. Each metal bar measured 3 feet long and weighed 15 pounds. A foreman stood at the corner of the brick building, holding a brass whistle in his hand. He blew a sharp note, sending a high-pitched sound through the trench. At the exact sound of the whistle, the 100 men pushed their steel bars in a simultaneous horizontal circle. The synchronized physical rotation turned the threaded iron shafts exactly 1/4 of a turn. The mechanical advantage of the inclined metal plane pushed the solid oak beams straight upward. The entire brick building rose 1/16 of an inch above the original fieldstone foundation. The synchronized turning distributed the massive physical weight evenly across every single cast-iron jack screw. The men completed another quarter turn with their steel crowbars, raising the heavy masonry walls, inch by inch, into the humid summer air. They stopped pushing the steel bars when the vertical iron screws reached their maximum physical extension of 14 inches. The crew rapidly built a second layer of wooden box cribs beneath the suspended oak beams. They lowered the vertical jack screws, transferring the 600 tons of weight directly onto the interlocking hemlock wood. The workers repositioned the cast iron base plates on top of the taller wooden towers and continued the lifting sequence. They turned the iron threads until the ground floor doorways of the building sat perfectly level with the elevated cedar block sidewalks. Local masons arrived at the site, carrying rectangular red clay bricks and wooden buckets filled with wet lime mortar. They laid the new clay bricks in overlapping horizontal courses underneath the suspended structure to build a permanent new foundation wall. The wet lime mortar cured in the open air, hardening into a solid calcium carbonate bond. The laborers reversed the rotation of the jack screws, lowering the heavy building exactly onto the new brick walls. The partnership of Ely, Smith, and Pullman elevated dozens of these large masonry structures throughout 1859. The firm kept the heavy commercial buildings completely intact during the entire physical lifting process. The flat glass panes remained firmly secured inside the wooden window frames. The interior plaster walls maintained their smooth, unbroken surfaces. The intact elevation of these individual structures provided the engineering firm with the necessary financial capital and physical equipment to attempt larger commercial projects. These individual building lifts culminated in a massive joint venture the following year. In 1860, a consortium of 6 engineers co-managed a project to elevate an entire continuous row of buildings at one single time. The engineering team included James Brown, James Hollingsworth, and George Pullman. The men signed a commercial contract to raise half a city block located on Lake Street between Clark Street and LaSalle Street. This continuous masonry row of shops and offices measured 320 feet long. In the spring of 1860, a consortium of 6 civil engineers combined their physical equipment to execute a single municipal lifting contract in Chicago, Illinois. The engineering team included James Brown, James Hollingsworth, and George Mortimer Pullman. The 3 other members of the consortium brought their own cast-iron jack screws, steel crowbars, and heavy white oak timbers to the joint commercial venture. The property owners along Lake Street hired this specific group of 6 engineers to elevate half of a commercial city block simultaneously. This massive elevation project targeted the continuous row of commercial structures located on the north side of Lake Street, positioned directly between Clark Street and LaSalle Street. The entire masonry row measured 320 feet long and covered almost 1 full acre of land. The continuous block consisted of individual 4-story and 5-story commercial buildings adjoining one another. Masons originally constructed these connected shops and offices using locally fired red clay bricks, thick lime mortar, and heavy limestone facade blocks. The builders of the block utilized shared party walls between the adjacent commercial properties to reduce construction costs and maximize interior space. A party wall consists of a single structural brick partition serving as the load-bearing support for 2 separate, adjoining buildings. The thick oak floor joists of 2 neighboring shops rested directly inside the exact same 18-inch thick brick wall. The hardened white lime mortar bonded the red clay bricks of the 320-foot row into one single continuous physical mass. Any vertical movement applied to one specific building transferred the physical force directly into the shared brick party walls. Elevating a single structure independently caused the interconnected lime mortar joints to snap, fracturing the masonry of the adjacent building. The shared structural walls forced the property owners to elevate the entire block of buildings at exactly the same time. The newly elevated cedar block paving on Lake Street sat 4 feet and 8 inches higher than the original ground floors of the commercial row. Surface water flowed from the raised wooden street directly down the exterior stone stairs into the lower brick entrances. The retail shops inside the row sold printed paper goods, heavy textiles, and forged metal hardware. The shop owners required their front entrances to sit completely level with the public wooden sidewalks to facilitate the loading of their heavy physical merchandise. The 6 engineers established a combined physical headquarters on Lake Street to calculate the structural load of the massive masonry row. The engineers measured the total volume of the red clay bricks, the limestone facades, the oak framing timbers, and the heavy slate roof shingles. They added the physical weight of the interior commercial goods, including heavy cast-iron printing presses and stacked wooden crates of inventory. The calculations yielded a total combined weight of 35,000 short tons for the 320-foot continuous block. The engineers ordered manual laborers to excavate a continuous dirt trench beneath the entire length of the 320-foot row. Hundreds of workers carrying flat steel shovels dug into the wet blue clay along the Lake Street foundation. The laborers removed tons of saturated earth, exposing the original fieldstone foundations of the connected shops. The freshly dug clay smelled of stagnant river water and decomposed root fibers. The workers laid flat, wide planks of eastern white pine into the muddy trench bottom. They covered the entire 1-acre physical footprint with these wooden boards to distribute the extreme downward pressure over the soft soil. Horse-drawn wooden freight wagons arrived daily at the Clark Street intersection, carrying heavy structural lifting equipment. The draft horses pulled loads of 6-inch square eastern hemlock timbers cut to uniform 4-foot lengths. The workers carried these 40-pound hemlock timbers down the steep dirt inclines into the excavated trenches. They stacked the square logs at precise 90-degree angles to build hollow wooden box cribs. The engineers spaced these wooden support towers uniformly across the entire 1-acre subterranean space. Masons descended into the trenches carrying heavy forged steel chisels and iron mallets. The masons chipped away the original white lime mortar at the lowest course of the brick walls, carving square holes completely through the masonry. The laborers inserted heavy white oak crossbeams through these freshly cut holes. The ends of these solid oak timbers extended outward from the brick walls and rested directly above the hemlock box cribs. The massive weight of the 35,000-ton structure required an unprecedented volume of mechanical lifting devices. The consortium of 6 engineers combined their entire inventories of cast-iron base plates and threaded iron screw shafts. Wagons transported thousands of these heavy iron machines from the separate workshops to the Lake Street worksite. Workers coated the spiraling metal threads of every single iron shaft with thick, yellow-rendered animal fat. The thick grease reduced the physical friction between the moving metal parts. The laborers placed the cast-iron base plates squarely onto the flat tops of the wooden box cribs. Each base plate weighed 50 pounds and contained a circular threaded hole measuring exactly 3 inches in diameter. They inserted the greased vertical iron shafts into the threaded circular holes of the base plates. The men adjusted the height of the metal threads until the flat top of each iron screw pressed directly against the underside of the inserted oak crossbeams. The dense blue clay holding the heavy building required the lifting points to sit very close together to prevent the soil from collapsing under the concentrated pressure. The engineers placed the cast iron assemblies at highly concentrated intervals along the 320 feet of foundation walls. The massive scale of the physical preparation consumed weeks of manual labor during the early spring of 1860. The workers completed the continuous wooden track and the insertion of the oak beams under the interconnected commercial shops. The structural load of 35,000 short tons of brick and stone now rested directly above the metal machines, requiring the engineering team to position 6,000 jack screws and send 600 men down into the dirt trenches. In the spring of 1860, the continuous masonry row on Lake Street contained 35,000 short tons of physical weight. The structures consisted of individual red clay bricks measuring 8 inches long, 4 inches wide, and 2 1/4 inches thick. The builders originally stacked these clay bricks to form exterior structural walls reaching up to 5 stories high. Thick limestone blocks imported from regional quarries formed the heavy front facades facing the elevated Cedar Street. Inside the commercial row, wide oak floor joists spanned the distances between the shared brick party walls. These interior oak beams measured 3 inches thick and 12 inches deep, carrying the heavy loads of cast-iron printing presses, heavy glass display cases, and stacked wooden crates of merchandise. The 6 engineers of the lifting consortium directed their crews to transfer this entire physical mass onto the temporary wooden support system. The laborers placed exactly 6,000 cast-iron jack screws directly under the thick oak crossbeams supporting the 320-foot brick wall. The workers positioned these metal machines at exact intervals along the continuous trench. The engineers spaced the cast-iron base plates closely together on top of the wooden hemlock cribs, placing the flat metal edges within an inch of one another. Each of the 6,000 metal base plates weighed 50 pounds. The solid iron lifting shafts measured 3 inches in diameter and featured deep, spiraling cut threads. Workers coated the 6,000 metal threads with hundreds of pounds of yellow-rendered animal tallow. The thick grease coated the iron surfaces, keeping the dense metal parts sliding smoothly against one another under the extreme downward physical pressure. The mathematical distribution placed approximately 11,666 pounds of structural weight directly onto each individual iron jack screw. The engineering consortium hired exactly 600 local laborers to operate the lifting machinery. The men descended the steep wooden staircases from the elevated cedar street down into the excavated dirt trenches. The 6-foot-deep trenches trapped the cool, damp air near the wet clay, maintaining an ambient temperature of 55 degrees Fahrenheit. The dirt walls smelled of wet river silt and decaying root fibers. The 600 workers spread out along the entire 320-foot subterranean corridor and the intersecting side trenches. The engineers assigned exactly 10 specific cast-iron jack screws to each individual laborer. The workers stood in the wet mud directly beside their assigned metal machines, wearing heavy leather boots to cover their feet from the saturated earth. The wooden floorboards of the commercial buildings completely covered the deep dirt trenches, sealing the natural sunlight above the ground level. To illuminate the physical space, the workers placed tin lanterns on top of the wooden box cribs. The lanterns burned liquid whale oil, emitting a yellow flame that cast sharp shadows across the brick foundation walls. The burning oil released a heavy, fishy odor into the confined air. The men carried heavy forged steel crowbars down into the dirt trenches. The workers inserted these 3-foot solid steel bars directly into the square heads of the vertical iron screw shafts. Each 15-pound steel bar provided the exact physical leverage required to turn the threaded iron against the immense downward weight. The engineers divided the 320-foot foundation into specific operational sectors to manage the massive labor force. The engineers instructed each worker to follow a precise physical sequence to manage their 10 assigned machines. The worker gripped the steel bar inserted into the first jack screw. After completing the required horizontal turn, the worker pulled the 15-pound steel bar straight out of the square metal head. The man then walked one step through the mud to the second jack screw in his assigned sequence. He inserted the steel bar into the circular hole of the second iron shaft. He repeated this exact physical extraction and insertion process for all 10 machines located within his specific 20-foot section of the trench. The overlapping physical movements of 600 men required strict spatial coordination to maintain exact physical clearance between the swinging steel crowbars. The 6 lead engineers, including James Brown, James Hollingsworth, and George Pullman, stood at strategic intersecting points within the dirt trenches. The engineers employed a network of foremen positioned every 50 feet along the continuous foundation wall. The foremen held brass whistles in their hands, serving as the sole method of communication above the physical noise of the active work site. The foreman watched the groups of laborers assigned to their specific sections, verifying that every single man stood in the correct physical position beside his first assigned jack screw. The entire continuous row of brick and stone rested directly on the flat metal tops of the 6,000 iron shafts. The original fieldstone foundation sat completely detached from the lowest course of red clay bricks, separated by a visible physical gap of 1 inch. The 600 men gripped the cold steel crowbars with their bare hands or heavy leatherwork gloves. The men stood entirely beneath the 35,000 tons of suspended masonry, listening to the subtle creaking sounds of the compressed hemlock box cribs settling into the damp earth. The physical weight of the continuous commercial block pressed straight down on the greased metal threads. The engineering team required absolute perfect synchronization from the 600 manual laborers to maintain the exact horizontal alignment of the rigid lime mortar. The men stared straight ahead at the cast iron machines, waiting for the high-pitched sound of the brass whistles to initiate the upward movement. The lead foreman stood at the intersection of the excavated dirt trench near Clark Street. He placed a brass whistle between his lips and exhaled, sending a high-pitched note echoing through the 320-foot subterranean corridor. The sound waves traveled through the 55-degree damp air, reaching the laborers at the far LaSalle Street end a fraction of a second later. At the exact sound of the whistle, 600 manual laborers stepped forward in the wet blue clay. The men pushed their 15-pound solid steel crowbars in a horizontal arc. The synchronized physical force rotated the first set of 600 cast-iron jack screws exactly 1/4 of a full turn. The spiraling metal threads ground against the 50-pound cast-iron base plates, converting the lateral movement of the laborers directly into vertical lift. The entire 35,000-ton commercial block rose exactly 1/16 of an inch into the air. The workers pulled the steel bars out of the square metal heads of the jack screws. The laborers walked 1 step to their right, leaving 1-inch deep impressions from their leather boots in the wet trench floor. They inserted the steel bars into the circular holes of the second iron shafts in their assigned sequence and waited in the damp air. 10 seconds later, the foreman blew the brass whistle a second time. The 600 men pushed the steel bars again, rotating the second set of 600 iron jack screws. The continuous masonry row elevated another 1/16 of an inch above the original fieldstone foundations. The men repeated this physical extraction and insertion sequence 10 times, cycling through all 6,000 jack screws located beneath the Lake Street buildings. Completing 1 full cycle across the 10 machines raised the entire interconnected brick structure exactly 5/8 of an inch. The labor force maintained this mechanical sequence for 10 hours each day. The physical exertion of pushing the steel bars caused the workers to sweat, releasing body heat into the confined dirt trenches. The rotation of the 3-inch iron threads generated physical friction inside the cast iron base plates. This mechanical friction heated the metal, melting the yellow rendered animal tallow into a liquid oil. The liquid grease dripped down the sides of the iron shafts and pooled onto the raw wood of the hemlock box cribs. The yellow tallow turned dark black as it mixed with the microscopic iron shavings, scraping off the heavy metal threads. The immense downward pressure of the continuous brick walls compressed the 6-inch square eastern hemlock timbers supporting the machines. The straight grain of the hemlock wood resisted splitting under the vertical force. The wood fibers compressed downward, reducing the overall height of each box crib by a fraction of an inch under the 35,000 tons of structural weight. The flat wooden planks absorbed the minor physical discrepancies in the lifting heights of the adjacent metal screws. This structural flexibility protected the brittle white lime mortar, connecting the thousands of red clay bricks forming the facades above the ground. By the end of the first 10-hour shift, the 600 laborers elevated the 320-foot row exactly 12 inches. When the vertical metal threads reached their maximum physical extension of 14 inches, the laborers stopped turning the steel bars. The men carried additional square hemlock logs into the trenches to build the wooden box cribs higher. They lowered the iron screws, placed the cast iron bases on top of the new wooden layers, and resumed the lifting sequence. As the wooden sills and brick walls rose higher into the air, local masons climbed down the steep wooden staircases into the excavated dirt trenches. The masons carried rectangular red clay bricks and wooden buckets filled with wet lime mortar. The local masons mixed the lime mortar directly in the trenches, using flat wooden paddles. They combined 3 parts of dry river sand with 1 part of slaked lime, adding fresh water drawn from the Chicago River. The chemical reaction of the slaked lime hydrating in the water released physical heat, warming the wet mixture to 80 degrees Fahrenheit inside the wooden buckets. The workers constructed new foundation walls directly underneath the suspended white oak floor sills. The masons laid the clay bricks in overlapping horizontal courses, while the 600 men continued to operate the iron jack screws just 2 feet away. The smell of the wet alkaline mortar, mixed directly with the heavy odor of the burning whale oil lanterns, illuminating the subterranean worksite. The engineering team of James Brown, James Hollingsworth, and George Pullman supervised the operation continuously throughout the spring of 1860. The foremen blew their brass whistles every 10 seconds, measuring the exact timing using USA-manufactured brass pocket watches. The engineers held canvas tape measures marked with 1-inch increments against the rising brick walls. They verified the exact vertical progress at 50-foot intervals along the entire 320-foot length. The coordinated turning of the 6,000 screws maintained a perfectly level horizontal plane across the entire 1-acre physical footprint of the commercial row. The continuous physical labor lasted for exactly 5 days. Over the course of these 5 days, the 600 men elevated the 35,000-ton structure, a total distance of 4 feet and 8 inches. The ground floor entrances of the commercial block now sat completely flush with the newly elevated cedar block street level. The masons finished laying the final courses of red clay bricks, completing the new permanent structural support walls beneath the interconnected shops. The laborers reversed the rotation of the 6,000 iron jack screws by pulling the steel crowbars backward. The metal threads lowered the heavy white oak beams exactly 1 inch, transferring the complete structural weight of the block onto the freshly cured lime mortar. The men pulled the cast iron base plates and the heavy steel crowbars out of the dirt trenches, loading the equipment into horse-drawn freight wagons on Lake Street. The draft horses pulled the wagons over the wooden street blocks, carrying the iron machines back to the respective engineering workshops. The Common Council of Chicago sent municipal building inspectors to review the structural integrity of the newly elevated commercial block. The inspectors verified the vertical alignment of the shared brick party walls using lead plumb bobs attached to cotton strings. The lime mortar joints contained 0 new fractures, and the plate glass windows remained firmly secured inside their wooden frames. During the entire 5-day lifting sequence, the retail shops located inside the rising masonry walls maintained their daily commercial operations. During the 5 days of the Lake Street elevation in the spring of 1860, the retail merchants operating inside the 320-foot brick row maintained their standard commercial hours. The shop owners unlocked their front doors at 8 o'clock in the morning and closed the latches at 6 o'clock in the evening. The businesses occupying the ground floor included dry goods merchants, heavy hardware purveyors, and paper printing offices. The owners sold bolts of dyed cotton cloth, forged iron nails, and printed daily newspapers. To accommodate the customers entering the active work zone, carpenters constructed temporary wooden gangways. The carpenters nailed 2-inch thick white pine planks together to form slanted ramps. These wooden ramps connected the newly elevated cedar block street directly to the original wooden thresholds of the retail shops. Customers walked down these temporary pine ramps, gripping rough oak handrails as they descended into the recessed storefronts. Inside the brick buildings, the sales clerks stood behind long oak counters. The clerks exchanged USA minted copper cents and silver dimes for commercial goods. The wide pine floorboards beneath the leather boots of the customers moved upward exactly 1/16 of an inch every 10 seconds. The continuous physical lift occurred with precise, steady mechanical force. Clear liquid water, resting inside glass drinking cups on the oak counters, maintained a perfectly level surface. The water surface held completely flat, retaining its physical volume directly inside the glass rims as the entire building rose into the air. Glass bottles filled with dark brown liquid medicinal tonics sat on narrow wooden shelves lining the interior brick walls. The glass bottles remained entirely stationary on the wooden planks. The gas lighting fixtures, bolted directly into the plaster walls, burned a steady blue flame. The flames maintained a constant shape during the vertical motion of the masonry structure. The physical activity of the 600 laborers working in the dirt trenches translated into audible sounds on the retail floor. The customers and clerks heard the high-pitched notes of the brass whistles blowing through the wooden floorboards. Following each whistle blast, a low, collective grinding noise traveled upward through the pine planks. The cast-iron threads turning against the cast-iron base plates created a deep mechanical vibration. The physical friction of the 6,000 metal jackscrews produced a low-frequency hum throughout the interior spaces of the commercial row. The 6-inch square hemlock timbers, supporting the entire weight of the structures, groaned under the 35,000 tons of physical pressure. The wood fibers, compressing in the dark trenches, released the smell of fresh-cut sap up through the gaps in the floorboards. As the brick row elevated steadily at a rate of 1 inch per hour, the physical height of the front doorways changed in relation to the stationary street. The entrance thresholds moved upward, decreasing the vertical distance between the shop doors and the cedar paving blocks. The carpenters returned to the exterior sidewalks every 3 hours, carrying forged steel hammers and iron nails. They pulled the iron nails from the temporary pine gangways and adjusted the physical slope of the wooden planks. The carpenters raised the bottom edges of the ramps to match the new elevation of the rising door frames. They hammered the iron nails back into the wood, securing the ramps at the newly adjusted angles. Customers continued to walk across these shifting wooden platforms throughout the afternoon, entering the rising shops, while the laborers turned the steel crowbars directly beneath their feet. The simultaneous elevation of half a city block drew crowds of spectators to the Lake Street commercial district. Thousands of Chicago residents gathered on the elevated cedar block sidewalks to observe the mechanical operation. The spectators stood on the newly packed river soil, watching the massive stone facades slowly ascend to meet their leather boots. The gap between the original fieldstone foundations and the rising brick walls expanded inch by inch, exposing the dark dirt trenches to the open air. By the fifth day of the operation, the 600 manual laborers raised the entire commercial row exactly 4 feet and 8 inches. The ground floor entrances sat perfectly flush with the raised cedar street. The carpenters dismantled the pine ramps using heavy steel pry bars and carried the loose boards away from the storefronts. Upon reaching the final elevation height of 4 feet and 8 inches, the engineering consortium opened the subterranean worksite to the gathered public. The engineers permitted the thousands of spectators to walk down the steep dirt inclines into the excavated trenches. The residents of Chicago walked on the flat white pine planks laid over the wet blue clay. The citizens navigated through the dense grid of 6,000 cast-iron jack screws supporting the 35,000 tons of brick and stone directly above their heads. The air inside the dark trenches held the distinct odors of the burning liquid whale oil and the thick yellow animal tallow dripping from the metal threads. The spectators reached out and touched the compressed hemlock box cribs and the cold iron bases with their bare hands. They observed the local masons laying the final courses of red clay bricks to form the new permanent foundation walls. The successful intact elevation of the Lake Street commercial block demonstrated the physical capacity of the engineering consortium to scale their lifting operations. George Mortimer Pullman and the partners of Ely, Smith and Pullman gathered their specific inventory of cast-iron jack screws from the Lake Street trenches. They loaded their heavy metal equipment into wooden freight wagons to prepare for an even larger structural elevation project. In the spring of 1861, the partnership of Ely, Smith and Pullman signed a new commercial contract to elevate the Tremont House Hotel. This specific structure occupied over 1 acre of land at the southeast corner of Lake Street and Dearborn Street, standing exactly 6 stories high. In 1861, the engineering partnership of Ely, Smith and Pullman won a commercial contract to elevate the Tremont House Hotel in Chicago, Illinois. The massive structure occupied over 1 acre of land at the southeast corner of Lake Street and Dearborn Street. The Tremont House measured 160 feet along Lake Street and 160 feet along Dearborn Street. Masons originally constructed the hotel using locally fired red clay bricks and heavy carved limestone blocks. The exterior load-bearing walls reached exactly 6 stories high, making the building one of the largest luxuriously appointed structures in the city at that time. The masons laid over 2 million individual red clay bricks to form the thick exterior walls and the interior partitions. The hotel contained 260 individual guest rooms, a large public dining hall, and a commercial kitchen equipped with heavy cast-iron cooking stoves. The municipal government of Chicago had recently raised the surrounding public roadways by adding 6 feet of dredged river soil and cedar paving blocks. This newly elevated street grade buried the original ground floor lobby doors of the Tremont House under 6 feet of dirt. Rainwater flowed down the raised cedar blocks and pooled directly against the lower brick walls of the luxury hotel. The hotel proprietors signed the commercial contract with George Mortimer Pullman and his 2 partners to elevate the entire 6-story brick mass. The engineering partnership agreed to raise the building exactly 6 feet into the air to meet the new cedar sidewalks, while maintaining the daily commercial operations of the luxury hotel. In the spring of 1861, George Pullman hired 500 local manual laborers to execute the physical elevation. The men arrived at the Tremont House carrying flat steel shovels and heavy forged iron pickaxes. The laborers dug directly into the wet blue clay surrounding the original fieldstone foundation. The men excavated the heavy, saturated earth and loaded the wet soil into wooden wheelbarrows fitted with iron-rimmed wheels. They pushed the loaded wheelbarrows up slanted pine ramps and dumped the excavated clay into horse-drawn wagons waiting on the elevated street. The workers continued digging until they created a continuous network of covered dirt trenches extending beneath the entire 1-acre physical footprint of the hotel. The physical dimensions of the 6-story brick building completely covered these deep dirt trenches, sealing the subterranean work zone in complete darkness. The laborers placed tin lanterns burning liquid whale oil on top of wooden stakes driven into the mud. The burning whale oil emitted yellow light onto the exposed red clay bricks and released a heavy, fishy odor into the confined 50-degree air. The dense clay held a high moisture content, emitting the strong scent of wet earth and stagnant water. Inside these covered tunnels, the workers laid flat planks of eastern white pine directly onto the muddy floor to create a load-bearing surface. The men carried 6-inch square hemlock timbers down the steep wooden staircases into the trenches. They stacked the 40-pound wooden beams at precise 90-degree angles, building hollow wooden box cribs along the entire length of the exposed fieldstone foundation. The engineering partnership transported exactly 1,000 cast-iron jack screws to the Lake Street work site. The workers hauled the 50-pound cast-iron base plates down into the trenches and placed them directly on top of the hemlock towers. The 1,000 base plates weighed a combined total of 50,000 pounds. George Pullman carried a canvas tape measure marked with 1-inch increments to space the machines. He walked through the damp tunnels, measuring exact intervals along the brick walls to position the metal lifting devices. The laborers inserted threaded solid iron shafts measuring 3 inches in diameter into the circular holes of the cast-iron base plates. They used flat wooden sticks to apply thick yellow rendered animal fat directly onto the spiraling metal threads. The cold trench air hardened the yellow grease onto the dark iron surfaces. Masons walked through the trenches, carrying forged steel chisels and heavy iron mallets. They swung the heavy mallets, driving the steel chisels into the brittle white lime mortar located at the base of the brick walls. The masons carved square holes completely through the 2-foot-thick masonry. The laborers inserted solid white oak crossbeams through these freshly cut holes, resting the ends of the heavy wood directly onto the flat metal tops of the vertical jack screws. The 500 manual laborers positioned themselves directly beside the 1,000 cast-iron machines. George Pullman assigned each individual worker to operate exactly 2 jack screws. The men received their daily wages in USA minted silver coins for this exact physical labor. They gripped forged steel crowbars measuring 3 feet long and weighing 15 pounds. They inserted the solid steel bars into the square metal heads of the vertical iron shafts. The 500 men stood in the wet mud directly beneath the thousands of tons of brick, limestone, and heavy oak framing. The men wore heavy leather boots, wool trousers, and thick cotton shirts. The engineering foreman stood at the intersecting corners of the subterranean tunnels holding brass whistles. A single foreman inhaled the damp air and blew a sharp, high-pitched note through his brass whistle. At the exact sound of the signal, the 500 men stepped forward and pushed their steel crowbars in a horizontal arc. The synchronized mechanical force rotated the 1,000 metal threads exactly 1/4 of a full turn inside the cast iron base plates. The greased iron threads converted the lateral physical force into direct vertical lift. The heavy white oak crossbeams pushed straight upward against the red clay bricks. The entire 6-story luxury hotel rose exactly 1/16 of an inch above its original fieldstone foundation. The 500 men pulled their steel bars out of the first machine, took a single step through the blue clay, and inserted the metal into their second assigned jack screw. While the manual laborers rotated the iron threads in the covered dirt trenches, the Tremont House Hotel remained fully operational directly above their heads, housing a full registry of sleeping guests and visiting United States senators in the luxurious upper rooms. During the spring of 1861, the Tremont House Hotel maintained its daily commercial operations while 500 laborers worked in the excavated dirt trenches directly below the floorboards. Hotel staff assigned rooms to hundreds of paying guests, including several United States senators traveling on the steam-powered locomotives of the Galena and Chicago Union Railroad. The guests slept on mattresses filled with compressed horsehair and covered with white cotton sheets. These guests rested inside the 260 individual sleeping quarters distributed across the upper 5 floors of the brick building. Below them, heavy white oak crossbeams pressed upward against the lowest courses of the structural masonry. The guests slept through the continuous mechanical rotation of the 1,000 cast iron jack screws. The iron threads turning inside the cast iron base plates generated a low physical vibration. This mechanical vibration transferred up through the thick oak floor joists into the pine floorboards and directly into the wooden bed frames. The physical vibration maintained a steady, continuous rhythm throughout the entire night. At dawn, the hotel guests descended the interior wooden staircases to the ground floor dining room. The hotel kitchen staff cooked morning meals on heavy cast iron stoves, fueled by burning anthracite coal. The burning coal heated the flat iron cooking surfaces to over 400 degrees Fahrenheit. The cooks cracked raw eggs and fried cuts of salt-cured pork in cast iron skillets. Waiters carried white ceramic plates filled with hot food directly to the guests sitting at long mahogany tables. The waiters poured dark roasted coffee from silver pitchers into ceramic cups. The liquid coffee maintained a perfectly flat horizontal surface inside the cups. The perfectly synchronized lifting of the 6-story brick building kept the mahogany dining tables completely level on the pine floors. The 500 manual laborers standing in the damp dirt trenches turned their 15-pound steel crowbars exactly 1/4 of a rotation every 10 seconds. This synchronized mechanical force raised the entire dining room 1/16 of an inch with each collective push. The guests sitting at the mahogany tables looked out the ground floor plate glass windows toward the intersection of Lake Street and Dearborn Street. On the first day of the elevation project, the bottoms of these window frames sat completely flush with the newly elevated cedar block sidewalks. Pedestrians walking on the street outside stepped at the exact same physical elevation as the guests eating at the dining tables. By the second day of the continuous lifting process, the 500 laborers had rotated the 1,000 iron screws enough to lift the building 24 inches into the air. The guests looking through the glass windows now observed the Cedar Street paving dropping 2 feet below their direct line of sight. The pedestrians walking on the cedar blocks outside now looked upward to see through the ground floor windows. The vertical movement of the massive brick structure continued at a steady rate of 1 inch per hour. To maintain pedestrian access to the hotel lobby during the multi-day lift, hotel carpenters constructed temporary wooden staircases at the main entrances. The carpenters nailed 2-inch thick eastern white pine planks together to form the flat steps and the side handrails. As the ground floor lobby rose higher into the air, the carpenters added additional wooden steps to the bottom of the staircases. They attached new pine treads every few hours, connecting the rising door thresholds to the stationary cedar street below. The luxury hotel required a continuous supply of fresh municipal water and a functional drainage system for the 260 guest rooms. Plumbers installed flexible lead pipes measuring 1 inch in diameter to connect the stationary underground municipal water mains to the rising internal copper pipes of the hotel. The soft lead material stretched and uncoiled slowly as the physical distance between the street and the building expanded. This continuous physical connection allowed the guests to turn brass faucets in their wash basins and receive flowing water, while the brick walls moved vertically around them. The 500 manual laborers operated the cast iron jack screws for exactly 5 days and 5 nights. The men worked in specific 12-hour rotating shifts to maintain the continuous mechanical upward pressure on the building. At the end of the final shift, the heavy white oak crossbeams sat exactly 6 feet above the original fieldstone foundations. The ground floor windows of the Tremont House now rested a full 6 feet above the heads of the pedestrians walking on the cedar sidewalks. The hotel guests walked down the extended wooden staircases to reach the public street. Inside the excavated dirt trenches, local masons arrived carrying rectangular red clay bricks and wooden buckets of wet lime mortar. The alkaline mixture cured rapidly in the damp air of the trenches. The masons laid the fired clay bricks in overlapping horizontal courses, building a new permanent foundation wall directly beneath the suspended oak sills. The new masonry wall measured exactly 72 inches tall, matching the precise physical height of the completed lift. The laborers in the dirt trenches reversed the rotation of the forged steel crowbars. They pulled the heavy steel bars backward, lowering the 1,000 iron screws exactly 1 inch. The complete structural weight of the 6-story hotel transferred from the temporary hemlock box cribs directly onto the newly cured lime mortar of the foundation walls. The workers pulled the steel crowbars out of the square metal heads and carried the cast iron baseplates out of the dark trenches. They loaded the 50,000 pounds of iron machinery into horse-drawn freight wagons parked on Lake Street. The intact elevation of the massive Tremont House established the engineering feasibility of lifting heavy commercial structures while maintaining daily business operations. The successful completion of this 6-story brick hotel lift prompted other engineers to scale the physical process for entirely different building materials. In November 1865, James Hollingsworth and his new business partner Coughlin secured a commercial contract to lift the massive Robbins Building, a commercial structure built with an internal frame made entirely of heavy cast iron. In November 1865, the engineering partnership of James Hollingsworth and a man named Coughlin secured a commercial contract to elevate the Robbins Building in Chicago, Illinois. The Robbins Building stood at the intersection of South Water Street and Wells Street. Builders constructed this specific commercial structure using an internal framework made entirely of cast iron columns and wrought iron floor beams. Foundry workers poured molten iron into packed sand molds to form these heavy vertical support columns. The building measured exactly 150 feet long and 80 feet wide. The exterior masonry walls extended 5 stories high into the air. The heavy cast-iron internal framing, the exterior brickwork, and the interior commercial goods combined to create a total structural weight of 27,000 tons. The original architectural design of the Robbins Building included 230 linear feet of heavy stone sidewalk attached directly to the exterior foundation walls. The property owners required the engineering team to lift this thick stone sidewalk simultaneously with the 5-story iron structure. James Hollingsworth and Coughlin hired hundreds of local manual laborers to excavate the dirt trenches beneath the cast-iron columns. In November 1865, the ambient air temperature in Chicago dropped to 40 degrees Fahrenheit. The laborers used flat steel shovels with solid ash wood handles to dig into the frozen topsoil and the dense blue clay below. The iron blades scraped against buried rocks, emitting sharp metallic scraping noises. The cold clay released the distinct scent of trapped river silt and decaying root fibers into the excavated trenches. The laborers laid flat planks of eastern white pine onto the damp trench floor. They stacked 6-inch square hemlock timbers on top of the pine planks to construct hollow wooden box cribs. The workers built these interlocking wooden towers directly beneath the heavy cast-iron foundation columns. The engineering team purchased exactly 1,584 cast-iron jack screws to handle the concentrated weight of the 27,000-ton structure. Each heavy jack screw supported approximately 34,000 pounds of physical weight during the lifting process. The laborers carried the 50-pound cast-iron base plates down into the 50-degree dirt trenches and placed them directly onto the flat tops of the hemlock cribs. The men inserted the solid iron screw shafts into the circular holes of the base plates. The continuous iron threads measured exactly 3 inches in diameter. The workers applied rendered animal tallow to the spiraling metal threads. The 40-degree ambient air hardened the yellow grease into a thick, waxy paste on the cold iron surfaces. The laborers inserted thick white oak crossbeams directly between the flat metal tops of the jack screws and the heavy cast iron floor sills of the building. The massive weight of the Robbins Building transferred directly onto the 1,584 metal lifting machines. Hollingsworth and Coughlin stationed the hired laborers at specific intervals along the dirt trenches. The men held solid forged steel crowbars measuring 3 feet long and weighing 15 pounds. The iron-framed Robbins Building possessed a rigid physical structure. The crystalline structure of cast-iron columns fractures under uneven physical stress. The engineering team required the hundreds of laborers to execute perfectly synchronized movements to maintain the rigid alignment of the iron beams. A foreman stood at the corner of the subterranean trench and blew a sharp, high-pitched note through a brass whistle to coordinate the manual labor. At the exact sound of the whistle, the laborers pushed the steel crowbars in a horizontal arc. The coordinated physical force rotated the 1,584 iron threads exactly 1/4 of a full turn inside the cast-iron base plates. The heavy white oak crossbeams pushed upward against the cast-iron foundation. The 5-story Robbins Building, along with the 230 feet of attached heavy stone sidewalk, separated from the underlying earth. The continuous stone sidewalk consisted of solid limestone slabs measuring 6 inches thick. The entire structure, including the exterior stone perimeter, rose exactly 1/16 of an inch into the cold air. The men pulled their 15-pound steel bars out of the square metal heads, walked one step through the cold blue clay, and inserted the metal into the next assigned jack screw. The manual laborers continued this synchronized turning sequence for 3 consecutive days. The men rotated in specific 12-hour shifts to maintain continuous upward mechanical pressure on the heavy building. The internal cast iron columns remained perfectly vertical during the entire physical elevation. The thick stone sidewalk outside the ground floor windows moved upward concurrently with the internal iron floors. At the end of the 3rd day, the laborers had turned the metal threads enough to raise the 27,000-ton building a total distance of 27½ inches. The ground floor entrances of the Robbins Building and the attached stone sidewalk now sat perfectly flush with the newly elevated grade of South Water Street and Wells Street. Local masons carried fired red clay bricks and wooden buckets of wet lime mortar down into the excavated dirt trenches. The wet alkaline mortar cured in the cold November air, forming a solid calcium carbonate bond. The masons laid the bricks in overlapping courses to build new permanent support piers directly underneath the cast iron columns. They constructed a continuous brick foundation wall to support the newly elevated 230 feet of stone sidewalk. The manual laborers reversed the rotation of the steel crowbars, lowering the iron screws exactly 1 inch. The complete physical weight of the 5-story iron structure transferred from the Hemlock box cribs directly onto the newly cured brick and mortar. The laborers extracted the 1,584 cast iron jack screws from the dirt trenches and loaded them into horse-drawn freight wagons. The completion of the Robbins Building elevation finalized the raising of the Central Commercial District. The municipal government of Chicago permanently maintained this new elevated grade, keeping the cedar block streets and the ground floor building entrances resting 6 feet above the water level of Lake Michigan. The installation of the above-ground gravity-fed sewer pipes beneath these raised streets directed the heavy wastewater out of the residential neighborhoods and pushed the liquid waste directly into the flowing current of the Chicago River. The continuous outward flow of this wastewater pushed the municipal pollution directly into the drinking water intakes located in Lake Michigan, forcing the city engineers to begin planning a 2-mile-long physical tunnel dug directly beneath the lake bed.